Good evening, everyone. Great to see so many of you here tonight. Thank you all for joining us. And welcome also to those of you on our live stream channels. My name is Anita Gajdetsky, and I work with the American Meteorological Society, the AMS. I am also the founder of this public speaker series, which is now in its third year. We have a lot of interesting science to cover here tonight, so I'll be brief. But I do want to give you all a quick background on the AMS and why we created this series of talks. The AMS was actually founded here in Massachusetts back in 1919 at the Blue Hills Observatory in Milton. I'm sure some of you may know, Blue Hills Observatory contains the oldest continuous weather record in all of North America, dating back to 1885. So who are we, and what do we do? Well, our thousands of members work in many interesting spheres. In academia, the private sector, and government. We have broadcast meteorologists, research scientists, students, policymakers, and industry executives, all doing their bit to uphold the mission of the AMS. And our mission is to advance the knowledge in atmospheric and related sciences and in their technologies, applications, and services for the greater benefit of society. It's been doing this successfully for the last 100 years or so. One of its core values is the belief in the integrity of science and the scientific process. It's this wealth of scientific knowledge and expertise that I wanted to bring to you, the broader public. And that's why I created the speaker series back in 2019. I also firmly believe in the power of bringing people together to share conversation and to spark dialogue and ideas. I'm sure you all agree it can be very difficult these days watching the news. And yet, it's necessary as individuals and as a society to stay educated and informed. With this speaker series, our hope is to present the science in an accessible and easy to understand way. Although we won't sugarcoat the facts, we present them to you with an underlying sense of optimism and hope, since this is how we as humans need to feel in order to move forward in a positive and constructive way. We also want you to come away tonight knowing a little more about the nature of water and how it powers our weather than you did before you came in. And let's also remind ourselves, since it's very easy to forget when we get buried in our day-to-day lives, that our world is a beautiful one and we are all in it together. I'll just take a few moments now to introduce you to our moderator for the evening. Dr. Matt Sitkowski is the Science Editor-in-Chief at the Weather Channel, where he oversees the scientific content across multiple on-air and digital platforms. He's also part of the production team that won an Emmy Award for its immersive mixed reality broadcasts. You should definitely watch these if you haven't seen them yet. Matt received his PhD in atmospheric science from the University of Wisconsin-Madison, his Bachelor of Science in meteorology at Florida State University, and his Master of Science in meteorology at the University of Hawaii. He also worked at the National Hurricane Center in Miami and the Forecast Office Central Pacific Hurricane Center in Honolulu. This only scratches the surface of Dr. Sitkowski's experience, but certainly when it comes to precipitation and nature's power, he knows what he's talking about. Please join me in welcoming Dr. Matt Sitkowski.
Thank you, Anita. Thank you all for being here this evening. And also, I want to thank you to those joining on the streams as well. Two hydrogen atoms bounded by a single oxygen atom results in a tasteless, odorless, transparent substance we know as water. You know, it sounds rather simple, maybe a little bland, maybe somewhat boring, but nothing could be further from the truth. Water is the shape-shifting magician of the natural world, transitioning effortlessly between solid, liquid, and gas forms. It can be as dainty as a nearly microscopic speck of mist wafting in the wind, are as intricate as a one-of-a-kind, six-sided dendrite frozen into perfection, are as powerful as a raging stream overflowing its banks brought on by a deluge of heavy rain. This constant cycle of transformation is the very essence of life. It sustains ecosystems and it captivates our senses with its ever-changing wonders. Water is ubiquitous, it is perpetual, it is in this room tonight, it is a part of us. And tonight we're going to talk about its power in all of its various forms of precipitation falling from the sky. And first up will be the frozen kind, the power of snow. During his nearly 20 years of government service, Mike Fries has seen a lot of interesting weather events. But perhaps his most memorable was almost a year ago, as a historic blizzard took the lives of dozens of people in and around Buffalo. He certainly knows a lot about that event, because Mike is the acting meteorologist in charge for the National Weather Service office in Buffalo. For 5 years previous, he was the warning coordination meteorologist. He too holds a degree from the University of Wisconsin-Madison, his master's, and a BS in meteorology from St. Louis University. Mike will start here in just a second, but I want to remind you that we'll be taking questions at the end after all of the speakers, both in the room and those online. So please remember them as you hear the presentations. We want to have enough time to do that, so let's go ahead and get started. Please join me in welcoming meteorologist Michael Fries.
Good evening, everyone. I just thought I'd take you on a quick walk. Maybe it won't be that quick, maybe it'll be 15 or 20 minutes, on the way that we went about forecasting the historical blizzard that we had this past Christmas in Buffalo. First of all, I thought it would be important to actually talk about what makes a blizzard, because there's a lot of misinformation on this exact topic. And for the National Weather Service anyway, it's really just a few simple things. One, you have to have falling or blowing snow. Two, you have to have continuous or frequently gusting winds of 35 miles an hour or greater. You have to have a visibility of less than 1/4 of a mile. And the combination of those things needs to occur for a continuous 3 hours. That, simply put, is what makes a blizzard. Technically, snow doesn't even have to fall to have a blizzard. But if we take a look at some of the historical blizzards and not blizzards in Buffalo's past, we're going to turn the clock back all the way back to 1878 with the Great Christmas Storm of 1978, then move forward to the blizzard of 1977, which for people in Buffalo is sort of the blizzard of record. It's the one that everyone's parents and grandparents remember, and they talk about it as the worst storm that ever occurred. And we're going to talk about how comparing blizzards is sort of an esoteric endeavor, even if it's one you probably really shouldn't do at all. And then we'll talk about what people in Buffalo call the Snowvembers, so one in 2014 and 2022. So first, that Great Christmas Storm of 1878. So that lasted 5 days leading up to and through Christmas Day in 1878. Winds in that storm gusted up to 72 miles an hour in downtown Buffalo. There was 39 inches of snow in total, which makes that storm somewhat pedestrian for Buffalo. There were drifts of over 7 feet of snow in town, which blocked all railroad traffic at the time, so the city was reliant on sleighs to get around. How appropriate for Christmas, right? But what's important to note about this storm is this storm set many of the records that were broken last year during our blizzard in 2022. Now let's move forward to the blizzard of 77. This was an event that lasted 5 days from the end of January into early February, but what distinguished it very, very much so from many other storms was how cold the period going back to the previous October was in Buffalo. You can see that for every month leading into it here, we were in our top 10 coldest for that month on record. Not to mention the fact that Lake Erie was fully frozen before this blizzard began. Actually, Lake Erie had been frozen since December 14th of the previous year, which made it the earliest freeze date of Lake Erie on record. And just for a reference there, that's sort of a fully frozen Lake Erie. Yes, there are a few fissures in there and whatnot, but that's generally what it looked like. And not only was it cold for essentially 5 months leading into this event, snow occurred in every day in January. And in fact, it occurred every day going back to December 19th in Buffalo that year. So about 6 weeks where it snowed every single day. The snow depth before any snow fell during this event was 33 inches on the 28th of January. And because of the previous snows and blowing around of snow and whatnot, snow was actually touching the power lines in places already before this blizzard began. Not to mention the fact that about 20% of all cars in the city were abandoned because they couldn't get them out of the snow. This blizzard, though, even though it lasted a long time and whatnot, actually only 12.3 inches of snow fell from this. So that makes the snow that fell actually less than pedestrian for Buffalo. And in this event, blizzard conditions were continuous for 11 hours. That was the longest duration of blizzard. However, blizzard conditions occurred on 5 consecutive days with the wind speeds up to 69 miles an hour during this event as well. And here are some of the pictures from the blizzard of 77 that the parents and grandparents in Buffalo talk about. I know my former supervisor used to talk about sledding out of the window of her house, which apparently was not a lie. And you can see the other situations, such as the snow up to the power lines in the bottom middle picture there, which is something I really can't fathom myself, even still. Now moving forward to a little more modern comparison, the Snowvember events in 2014 and 2022. Snowvember of 2014 actually was 2 separate lake effect events that both occurred in pretty much the same spot in what we call the South Towns of Buffalo, which are essentially the southern suburbs. Luckily enough for us in the area, though, those tend to be a little bit less heavily populated than the northern suburbs. But in the first half of the event that lasted 3 days, we got about 5.5 feet of snow in that area, followed the next 2 days after that by another 3.5 to 4 feet, such that event totals in these areas reached about 7 feet over the course of 2 events. It stranded hundreds of cars on the New York State Thruway. The Bills game, sorry, I have to mention the Bills because I'm coming from Buffalo, was relocated to Ford Field in Detroit, which became a common theme again later on. But in that event, because as I mentioned, the snow was in the South Towns, Buffalo itself only saw 6.2 inches of snow. And because there was not really a lot of wind with this event at all, it was not a blizzard at all. And here are some of the pictures from it, 2014. I know the media love to show the stream off of Lake Erie into downtown. The 2 pictures there, especially the nighttime picture, is pretty powerful, as well as some of the abandoned cars on I-90 in Buffalo there that sort of just look like igloos. Glad that wasn't my car. Moving forward, now notice we're into 2022 now. So this is November of 2022. So we call this November number 2. This was an event from November 16th to the 21st, so only a month or so before Christmas last year. We had another big lake effect event that affected the Buffalo South Towns, but also crept up into the city. In this event, snow was falling at a rate of almost 6 inches per hour at the Buffalo Airport, which is right where our office is. And I was there when that occurred, and I have never seen anything close to that in my life. You couldn't see the cars in the parking lot from the door. And it's only a gap of, from me to this TV to get there, and you could see nothing. But we received a little over 3 feet of snow in the city of Buffalo, which makes it a decent snow. Unofficial measurements in the South Towns of Buffalo approached 7 feet of snow in this event, with widespread and continuous thunder snow in this event, because Lake Erie was still sitting at 52 degrees when this event started. Once again, the Bills chose to move their game to Detroit and Ford Field, but this too, even with all this snow and all the impact, was not a blizzard. And so here's some pictures for this. Matt, you should see the bottom middle picture there with the Wisconsin logo on it. But I'm not saying that's my backyard, but that's my backyard. And I will say this picture on the bottom left here is by the historic train station in Buffalo, which is where they host Dingus Day in Buffalo. And that snow was still there into the summer last year that they moved into that location. So moving forward to the event we all want to hear about, the Christmas blizzard. So we've heard some of the events you can compare it to, but this event lasted from December 23rd to the 27th last year. However, in the days leading up to it, subsequent to this November snow and before the Christmas blizzard, we actually had another lake effect event. This I like to call the forgotten snow between the two snows. It was a fairly modest event where the Buffalo South Towns got almost 2 feet of snow, and a little over between half a foot and a foot fell in the city itself. With lake effect snow warnings for this event still being in effect through December 20th, while our office was already trying to message something bigger coming. So in the days leading up to it, our office started to enumerate a whole lot of different things in all the products that we issue, from mentions in our hazardous weather outlook to finally putting out winter storm watches with blizzard conditions being possible on the 20th. On the 21st, we labeled it a once-in-a-generation storm ahead of time. A day later, we issued the blizzard warnings that mentioned 70-mile-an-hour winds in the blizzard warnings, as well as accumulations of 1 to 3 feet of snow. With a start time, you'll notice that start time between 7 and 9 a.m. That's a really bad time to start a snow on a weekday. We upped the wording a day later to increase the accumulations and mention wind chill factors of 20 degrees below zero. And this is what we were looking at as it rolled in. So we'll pay attention, first of all, to the low pressure developing basically at the intersection of Ohio, Indiana, and Michigan there. 1,001 millibars at this time. This is 0 Zulu on the 23rd of December. And I'm just going to walk you through 18 hours here. You can see we go from 1,001 to 992 6 hours later, to 982 6 hours later, and 6 hours after that, we're at 974. That is 27 millibars or hectopascals in 18 hours. We eventually got to 34 in 24 hours, which well exceeds what you need for a bomb cyclone at our latitude, which people talk about it being 24 millibars in 24 hours. That's not really the case at our latitude. It's probably more on the order of about 18. But needless to say, when you can call something a bomb cyclone as well as giving it the nomer of being a generational storm, it gets a lot of attention. So we knew this one was going to be very different. So on the 23rd of December, the blizzard started at 8:39 a.m. Notice the product that we issued before, between 7 and 9 a.m. I think that's pretty good. The blizzard lasted an unabated 37 continuous hours, with peak winds in downtown Buffalo reaching 79 miles an hour. At the airport in Buffalo, which is about 10 miles inland from Lake Erie, so you've got a lot of surface roughness, I guess, between the airport and the lake. It still was gusting 72 miles an hour, and at Niagara Falls, it was blowing 74 miles an hour. These gusts are strong enough that if they were sustained, it would be a Category 1 hurricane, but we won't get into that. So I just thought I'd show you the radar loop of what happened, and this is starting on the 23rd at about 7 in the morning or so, so right before the changeover from rain to snow. And there's an image every half hour. So on about the third image here, when I start this loop, I can't play the loop. Anyway, this is a radar loop that lasts 3 days. But you would see the band essentially setting up right over Buffalo, then sagging southward a little bit, then coming back up and sitting right over Buffalo, then going north of Buffalo into what we call the North Towns. And the North Towns of Buffalo are where the majority of the population is. Obviously, it's not as big as metropolitan Boston, but about 1.2 million people live in this area. And the vast majority of them either live in the city. Oh, I can see the thing down there, but I can't click it. There you go. So here we go. The event's starting. You'll see the band originally in the South Towns. It comes over the city, sits over the city for a very long time, with radar returns approaching and exceeding 40 decibels at times, which in pure snow is very impressive. And the band then moves into the North Towns of Buffalo, eventually gets all the way up to Niagara Falls. Well, in this time, in the South Towns of Buffalo, the sun is actually out. And it's doing its damage in Niagara Falls right now, and eventually comes sweeping back through town one last time to make us all really hate it even more, and eventually withers to a slow death in the South Towns as it falls apart and becomes less impressive to look at. Oh wait, there may be one more time it comes back. But just to note, these images are every half an hour, and we started on the 23rd. We're now on the 26th, so this is 3 days into it at this point. And it's still going, yeah. I promise it's almost done. All right, there we go. So these were the snow totals that we got, and these snow totals are impressive, especially for the North Towns of Buffalo, because as I always like to say at the office, it never snows in the North Towns, except when it does. That's actually where the heaviest snow for this event was, and in particular, one of the places that, when we get lake effect snow in the Buffalo area, that tends to be one of the least snowy places in the area is North Tonawanda. It actually ended up being our winner, if you want to be a winner, with 59.7 inches. At the airport in Buffalo, we got 51.9 inches. So that the sort of bracket between those two locations encompasses the vast majority of the population there. So you can imagine the catastrophe that unfolded with a blizzard that lasted the better part of four days, with almost 5 feet of snow having fallen on that location. Now let's talk about comparing this blizzard to the blizzard of '77 and some of the other ones. People tend to build these mental constructs of what a blizzard actually is, and I went through the whole definition of what a blizzard actually is. And those mental constructs don't really align with what that is. That blizzard in '77 built the mental construct for all the people in Buffalo of what it meant to be a blizzard, but these events were very different. Preceding the events especially were very different. In '77, we had multiple months of cold weather with continuous snowpack and continuous snow. In '22, we had really large events, but all of the snow melted between them. Every last drop except the piles. We had 7.5 feet of snow, or 7 feet of snow that fell in the South Towns in November. Within 10 days, all of that snow was gone. And then we had the event right before it that started to melt as well before this storm started. So they were very different, having them in a warm winter as opposed to a cold winter. But as we look forward to the future, this is sort of one of those things that we're noticing a lot more, is that there is a trend, a very marked trend, for more snow from lake effect events in and around Buffalo. However, the snow simply doesn't last on the ground. We are seeing an annual increase in snowfall, particularly lake effect snow, but a marked decrease in the days with snow cover. We continue to break records, though, with the snowfall that we get from these events. And this is an important thing to remember for the future, because I know the hot topic, we were all discussing it today earlier, is AI and how that feeds into weather forecasting and things like that. And these events will be difficult, whether we evolve our current modeling to handle them or we rely more heavily on AI. These are things that will need to be worked out for the future, because we just simply don't have a handle on how that'll work going into the future. And I thought I would end with some pictures from it. I can tell you about some of these places. That is right in the middle of downtown on the top left. The bottom right is a very heavy shopping area. And I don't know what was going on the bottom left, but I just really thought that was a cool picture. So I thank you, though, everybody.
Thank you, Mike. And I also want to thank your office for using that language in your warnings. the once in a generation, that really emergency managers, media made us realize that this was an upcoming event that folks are not used to. We will now expand our view of precipitation both in time and space. Dr. Gabriel Vecchi will discuss the mechanisms of precip variability and climate change. He is a professor in the Geosciences Department at Princeton University and is the director of the High Meadows Environmental Institute. His over 200 peer-reviewed publications focus on an understanding of short and long-term changes in the ocean and atmosphere, including weather extremes and global patterns of rainfall and drought. Dr. Vecchi has received numerous awards, including the U.S. Presidential Early Career Award for Scientists and Engineers. He received his PhD in oceanography and master's in applied mathematics from the University of Washington, and has an undergraduate degree from Rutgers. Let's welcome him to the stage.
All right, so I'm going to change a little bit the theme of the discussion, both looking at longer time scales, but also we're going to look at water largely through its absence, right? And it's in its invisible form that is very, very influential. So I'm going to talk about climate and its weather connections. Shown over here are two recent events. On the top, it was the 3-day rainfall for Hurricane Harvey. This was a hurricane that very analogous to the storm that parked itself over Buffalo. Harvey parked itself offshore of Houston and over a course of a few days dumped water directly on it. And it's been shown that the rainfall from Harvey was amplified because of global warming and also because of urbanization. And then below is the late 2021 heat wave in the Pacific Northwest. This was a heat wave that for people in Portland, Seattle, Vancouver, Victoria, they were not prepared for it because it was the type of heat wave that we've come to realize would have been practically impossible without global warming. So our infrastructure wasn't ready for it. People didn't have the air conditioning. We had a very tough situation to deal with. And so that's sort of the type of things we'd like to talk about. And I'll start by putting us into some longer-term context. This is a time series of the average temperature of our planet. This is looking over land and ocean, and it's arranged such that bars that are red and above that line are bars in which the temperature over the November to October was warmer than the 20th century average for that period. I did it for November to October so that we have the latest records on there. And what you should see is the early part of the record was largely below the 20th century average by a little bit. And I've put in a few dates in there along with political and cultural touchstones of there, the #1 song of the year. And in particular, 1976 was the last year that the temperature average over the year was as cold or colder than the 20th century average. That was a year when Ford was president, Carter just got elected, and Silly Love Songs by Wings was a #1 song that year. I don't know if any of you can hum that song in your head. I can't. I listened to it a few years ago to try and remember. I just can't remember it. So anybody that was born in 1976 or later, or late after 77 and later, has never been on this planet when the year was colder than the 20th century average. The planet has warmed, right? We're not waiting for global warming, we're living with it. Not only are we living with it, we're living with substantial global warming. Every one of the last 10 years was a part of the 10 warmest years since we started taking records in the 1880s. So we've been living through 10 of the warmest years. Yes, it hasn't been a nice sort of linear increase. There's stair steps. There's periods over which the world sort of looks to slow down, and then it accelerates the warming. One of the concerns is that this warming is going to continue. This warming is fueled by greenhouse gas increases in the atmosphere, but water is hidden in this warming as well. The main mechanism by which the planet warms is the response of water vapor in the atmosphere to the increases in greenhouse gases in the warming it drives. The amount of water vapor in the atmosphere depends on temperature, and water vapor, those two hydrogen atoms locked into that oxygen atom, is a really great absorber of infrared radiation, very powerful greenhouse gas. And so when you increase water vapor, you make the planet warmer, right? So global warming, the proximate cause is water vapor. The ultimate cause is CO2, right? So water is in this plot. Now we're going into the future and we're trying to understand the past, but we're not without tools. And this is one of the great things, right? To be optimistic. If this was happening and we had the technology of the 1700s, we'd be flying blind. We wouldn't understand atmospheric physics. We wouldn't understand ocean physics. We wouldn't have what we have now. And one of the great tools that we have now is a tool that was developed in large part by my colleague and friend, Suki Manabe, who was awarded one of the co-awardees of the 2021 Nobel Prize in Physics for inventing the climate model. We now have a tool that combines our understanding of physics, radiative transfer, chemistry, a few other things, to be able to tell us something about the future. So we're not flying blind. We have the ability to look into the future and perhaps change our behavior or adapt to it, or any number of things that we could do. And here is a figure from a paper by Manabe and Stauffer in 1980, where they said, what is the pattern of warming you should get from increasing greenhouse gases? This was a prediction of what we should be able to see. 1980, global warming wasn't yet clear. And one of the things that we have been predicting for quite a while is that the warming of our planet, when you increase greenhouse gases, shouldn't be uniform. It should have a pattern, a very clear pattern, that northern high latitude should warm more rapidly than the rest of the planet, that the oceans should warm more slowly. That was a prediction in 1980. We now have data, right? This is classic science. You make a prediction about how the world works. You wait along, and you see the science, and this is the pattern of warming that we've seen. So on the point of view of sort of agreement between a 1980s scientific figure and a modern satellite image, that's perfect agreement, right? We see this polar amplification, this minimum warming over the oceans. The physics for all of these is really interesting and relatively well understood, okay? So the other thing to keep in mind here is because of the polar amplification over land, when we're talking about 1 degree or 2 degree of global warming, we're talking about considerably more warming over land and over the northern hemisphere lands, right? Part of that is water vapor, right? Part of it is the land-sea temperature, heat capacity differences, a few other things, right? But we understand, we've made predictions, we've validated some of these predictions, and we can use these tools to understand the world. Now, it's not just mean warming that we expect in response to increasing greenhouse gases, but we also expect, and we've seen, that as you warm the planet, as you shift temperatures, the average temperature, variations about the average temperature, including extremely cold days and extremely warm days, also shift, that whole bell shape shifts, so that the odds of extremely warm days become much more likely, and the odds of extremely cold days become less likely. Also, the amplitude of the warmest days becomes warmer, and the amplitude of the coldest days is expected to become colder. The statistics of weather change with regards to temperature, and that's easy to understand. But the one that's really neat and involves water is that, remember, the carrying capacity of water by air depends on temperature. One of the consequences of increasing moisture in the atmosphere is you amplify the greenhouse effect, so you get more warming. Another consequence is the air is more moist, and so you're more efficient at concentrating water when you concentrate water to get rainfall. So we expect that the rainiest events should get wetter. But the counterintuitive result that is really, really cool is that you expect dry places and dry times to get drier. Because what is a dry place and a dry time? A dry place is a place where the atmosphere has moved moisture away from it. You've packed moisture into the atmosphere and you've moved it away from a dry place. That's how it becomes dry. If the atmosphere gets more efficient at holding water, then it is more efficient at moving water away from dry places and dry times. And so what we expect in a warming world is that dry places, shown here in the red, these are places where you have an expected increase in consecutive dry days or droughtiness. You see that the Mediterranean, which is a dry place, North Africa, you see that the southwestern United States, Australia, the southern deserts are all expected to become drier. So there's this sort of phrase that we use that in a warming planet, the wet get wetter and the dry get drier, right? It's this nod to the rich get richer, poor get poorer type thing. Now, what do these heat waves look like? Well, these heat waves in a warming world aren't a thing about the future. Here are just from, I believe it's 2019 on the bottom left, 2021 on the top left, 2022 in the top right, and then this past summer, August of 2023, bunch of heat waves that have occurred, right? These are happening now. These are covering large areas of our planet. Look at the April 2022 one. How much of our planet had temperatures above 30 degrees and even above 40 degrees Celsius? 40 degrees Celsius, if it was not fully dry, is above your capacity to sustain being out there, right? These are dangerous heat waves, and they're occurring in April in North India and Pakistan. That is a time of when the winter wheat is being harvested and grown. That's one of the breadbaskets. Look at the Midwest of the United States in 2023, another one of the breadbaskets. The odds of having big heat waves in a number of breadbaskets at the same time is going up. And if you couple it with the type of social and political disruptions that tend to happen, human beings do these things, right? So we sort of pulled one of the other breadbaskets out of the market recently, right? When somebody, due to political and military situations, you can imagine that there would be downstream consequences here, right? Now, what is causing these heat waves? There's now a process. It's called event attribution. There's a number of people doing this work. I sometimes get involved, others get involved. And what we do is we have a very clearly defined methodology, and almost in real time, we're able to ascribe how much of a given heat wave can be connected to global warming. Today's global warming, not the global warming in the future. And so for the 2022 Pakistan and North Indian heat wave in the spring, it was made 30 times more likely because of global warming. That's today's global warming, or 2022's global warming, not the end of the 21st century, right? If you look at the Pacific Northwest heat wave, the assessment was that it was virtually impossible with global warming. It still remains rare. This is the 2023 heat wave, 2021 heat wave in the Pacific Northwest is not something that we expect all the time going forward, but it went from being virtually impossible to something that can happen in a measurable way, right? Now, it's not just that the cold days are getting colder. The warm days are getting warmer. The cold days are also getting warmer. So this is data from observations. This is looking at all these weather stations around the globe. And what is shown here is how the temperature of the coldest day of the year has changed at each place. And the color coding is such that the deepest reds, the ones that are around the 4s and the 5s, are places where the coldest day of the year has warmed by about 4 to 5 times the rate by which the planet has warmed. So we still get cold days. I was bundled up before I came here, right? And then again, I come from New Jersey, so I'm not used to this. But the cold days are getting less cold. The cold days are days when we get snow. If they still continue to get less cold, but still below the freezing point, the atmosphere will have more moisture. And there's a possibility that you dump more snow when these things happen. Especially associated with all this, lakes are starting to freeze less. More open water, more possibility for this lake effect snow. Now, eventually, if this continues, maybe you'll cross that freezing point threshold more often and you won't need to worry about snow so much, but then you have to worry about winter rain. Anyway, you see that this pattern over here, that's that polar amplification again. Now, it's not just rain that we need to concern ourselves, it's drought. Drought is a complicated topic, but it ultimately involves a deficit of water. It's either not enough water for us to run our power plants, not enough water for us to have our recreation, not enough water for our salmon to run, not enough water for us to do our irrigation or run our cities. There are different definitions of drought, but they all don't involve not enough water. And a warming atmosphere will tend to give you more likelihood of drought and more extensive droughts. There was a paper that in 2007 predicted an imminent transition of the Southwest United States to a more arid climate. And recently, there's a very neat study involved combining both climate models that can sort of piece out the causes of different climate situations, as well as long-term records from different sediments that allow you to go back into prehistoric times. This starts in the year 800 of the Common Era and goes all the way to the recent era. And it sort of tries to compile what the droughtiness, so soil moisture, would be pointing down would be a drought period. And you can see that droughts have occurred, persistent multi-decade, even multi-century droughts have occurred in the history of the Western United States, going back into the Middle Ages. But the recent dry anomaly, the 2021 to 2000 anomaly, stands out. It is somewhat below the driest of the dry. And the authors here, Williams and Cook and Samaritan, were able to show that about 42% of the recent drying of the Western United States could be attributed to the warming of our planet so far. Now, we're not yet at a 1 degree, 1.5, so we're not yet at a 1.5 degree persistent world or a 2 degree persistent world or a 3 degree persistent world, and we're already seeing impacts on drought. Okay, what are we doing? Well, the good news is that there is action, right? One of the things that we're doing is there's, as a global community and also locally as individuals, the United States government, companies are working to decarbonize our economy, right? And that is a fantastic thing. It's exciting. It's a technological opportunity. It's really a curious thing. How do you transition your energy systems? It's also, there's a lot of opportunity to make money, right? But it is also a challenge because we are fundamentally altering the relationship between weather and our energy supply. For the carbon high intensity energies, our fossil systems, what matters was the weather millions of years ago. That's already fixed in time, right? Those energy sources are underground. Going forward, we're going to be moving to hydropower, more to wind, to solar. And the weather today over the last few weeks is going to matter much more to our energy supply. So we, in order to make this energy transition and make it cleanly, are really going to have to simultaneously invest in our ability to make assessments about the current and the future state of the atmosphere and ocean, improve our weather forecasts. If we want to gracefully transition our energy systems, we have to improve our weather forecasts, okay? And our understanding of the climate system. So, just in summary, the impacts of climate change on weather are already evident. Warm extremes are becoming more likely and will continue to do so. Global warming is baked into the system, even if we get to net zero, all right? Cold extremes become less likely. Warmer air means that increased wetting and drying, the dry get drier, wet get wetter. Now, this all gets complicated in a very local level when you start considering urbanization, the effect of non-greenhouse effects such as particle pollution, and natural variability, these fluctuations that we saw over the last few thousand years in the Western US, things like that are evident everywhere. But we know that we're changing the die we're playing with. We didn't fully know what the current die are or the recent die, but we're playing with a different set of die as we start thinking about the future. So just in closing, really quick, what can we do? Really the problem we find ourselves in is that we have economic activity, and that economic activity fuels our prosperity and well-being. That's, all of us are wearing clothes, or we're sitting in comfortable chairs, I'm speaking into a microphone, all wonderful. But a side effect of our economic activity is carbon emissions, which increases atmospheric CO2, which leads to climate changes, which has societal impacts, and that negatively can affect our prosperity and well-being. So what we would like to do as a society, as a civilization, is break those chains between our economic activity and the prosperity and well-being. This is a slide that I stole the idea from David Keith, a professor at the University of Chicago, but I thought it really sort of clearly does it. And so how can we do this? Well, there's solutions that are there already. Some of them are being put into place. Some of them are much more fanciful. But in order to break the link between economic activity and carbon emissions, we need to decarbonize our energy. In order to break the link between carbon emissions and atmospheric CO2, we need to capture CO2 and sequester it, if we can. Finally, I'll go focus on the final one. In order to break the link between climate change and societal impacts, negative societal impacts, we need to adapt. We need to build better, we need to build smarter, we need to have better forecasts. And then more recently, there's a lot of discussion. This is not something that is viable right now. Nobody's advocating for it right now, but it's worth studying. Breaking the link between atmospheric CO2 and some of the climate changes to buy us time. And that's this idea of geoengineering or solar radiation management as a way to temporarily buy us time if things got really bad. There's a lot of science on that, but who knows? Anyway, this is where we are, and there's paths forward. Thank you.
Thank you, Dr. Vecchi. Now, lastly, we can't talk about precipitation. We can't talk all about this water without talking about the oceans. After all, nearly 97% of all the water on Earth is found within them. Which brings us to our final speaker, Dr. Kim Cobb. She is the director of the Institute at Brown for Environment and Society, where she works with her coworkers to conduct groundbreaking research to solve our complex 21st century problems. Dr. Cobb works to advance our understanding of climate extremes and also has an emphasis on some coastal flooding as well. Among her many accolades is a National Science Foundation Career Award and a Presidential Early Career Award for scientists and engineers. And for those paying attention, we've got two of them in the room tonight. She received her BA from Yale University and her PhD in oceanography from Scripps Institute of Oceanography. So please join me in welcoming our last speaker, Dr. Cobb.
Thanks so much, Matt, and it's really a pleasure to be here. I can't wait to hear the discussion. So many of us are passionate about sharing our work, but it's really what we hear from you that drives so much of us, our work as well, and our understanding the priorities. So I just wanted to open with this amazingly evocative artistic graphic of the warming curve that Gabe showed going back to 1880 and noting that there's some very dark red lines on the far end of that, and we're about ready to add another very dark red line with the record of 2023. So, the oceans are vast and they contain most of the water. They also have taken up over 90% of the heat that we have baked into the Earth system from the emissions of greenhouse gases historically. So, talk about an ecosystem service, right? It doesn't get much better than that. And yet we see now that they are expressing more and more of that heat at the surface level. And this is an incredibly stark graphic of the warming that occurred during this fall. So this is September 2023. It was an all-time record for September of all time Septembers, and I'll show that in a second. But I want to just note that it's not just certain patches of the ocean. There are large, numerous large patches of the ocean that are registering extremely warm temperatures. And this is just taking, so Gabe showed a graphic of, I believe, October, November's through time. This is actually just a September back, month by month of each individual year since the beginning of the instrumental record. And you can see September 2023 just kind of leaping off the plot, inspiring some of my climate science colleagues to find new vocabulary to describe the hellscape that we find ourselves in with the pace of warming right now. So that's not a common phrase in climate science work. And Gabe talked about the capacity of the atmosphere to hold more water vapor, and squeezing that sponge yields a much better return in terms of the concentration of rainfall that we expect to occur in a warmer world. And this is something that's close to home here in New England. The extremely crippling and devastating floods that occurred in Vermont. And while they didn't have the kind of scientific attribution study that Gabe talked about, because the threshold for those is certain amount of damages and lives lost, they did estimate that this was less than 0.6% likely, even in a today climate. Very rare, and something that we know will accelerate going forward. And New England is, by the way, one of those regions where we have enough data to help us understand that we're one of the bullseyes for extreme rainfall. We see it already in the records. It's projected in models as well. And when we see that overlay of data showing us stuff and models telling us why, that is some of the most robust information that we can take to the bank and we should be using to help our communities prepare to stay safe and prosper in a warming world. So this is moving into October now. So this is a map that looks a little different, but similar in many ways. Vast regions of the ocean this last October registering all-time records. Those are the deepest reds on this plot. And you can see it's not just certain regions of the ocean, huge sections of the ocean's all-time record warming for October. And I just wanted to note that a good portion of that warming is actually happening in the tropical Pacific and tropical Atlantic. And we'll come back to both of those in a minute in talking about the kinds of extremes that were fueled by those record warming in those specific basins. And this is one of those graphs that we can show in terms of the power of the ocean to drive weather extremes. And this is the history, cumulative history of the North Atlantic hurricane season this year, which was projected to be a modest year at the outset, maybe hovering slightly around average. There's some competing forces in there. Very warm ocean temperatures would, of course, drive stronger hurricanes on average, and that's something that we saw going into the season projections. But these patches of warm oceans in the Pacific have a dampening effect on North Atlantic hurricane intensities. And yet, even so, at the end of this season, we can see that we're basically in a very active hurricane season. Where have the headlines been? Obviously, we've had a couple horrific headlines this fall, but actually most of these were not landfalling hurricanes. We can track them in the middle of the Atlantic basin, but you may not have experienced it as one of the most active seasons on records, but it actually was. So moving back to this graph and digging into the Pacific now, moving from the Atlantic to the tropical Pacific, you can see this vast swath of very high temperatures, record temperatures in the eastern Pacific basin. And this is where we get to talk about the ocean's role in driving one of the most horrific storms that have occurred this fall, which is Hurricane Otis, of course, a Category 5 record-breaking event which intensified very quickly over some of the warmest waters the Eastern Pacific has ever seen. Right in the, if I can go back, you can see that record warming temperatures right off the coast there. And it's as that storm passed over those extremely warm waters that we saw that rapid intensification to what became an extremely devastating, once-in-a-generation event, certainly, for communities that were ill-prepared. They have poor infrastructure, they have poor emergency planning and response. The total toll from this event will take probably years to uncover in its full dimensions, and certainly will be remembered for generations as a tipping point for some aspects of community resilience there. So I want to dig into the tropical Pacific because that's my expertise. And we are actually living through a climate extreme right now called an El Nino event. How many of you guys have heard about the El Nino event underway already? You guys are kind of the weather geek crowd, so that is a good calibration point. So we're starting to see it in the headlines now. It has been underway for a number of months now. We know it will continue for the next few months, give or take. And this is what it looks like from a satellite view from NASA, where remember, this is like half our planet we're looking at here. So when we see the extent of warming across the eastern to central Pacific, characteristic of an El Nino event, this is a very large amount of water that's heated up, and it is providing a change in the atmospheric circulation of our entire planet with this new heat engine parked across the equator in the tropical Pacific. So this is not a one-off, right? El Niños occur every few years. It's one of the natural climate cycles that, as far as we have records for into the past, we see the evidence of El Niños. As long as the plates are in their current configuration, we see evidence of El Niños coming and going. However, the last record-breaking event was in 2015-2016. Topped all the charts. And this one is coming quickly on its heels, if you will, kind of begging the question about whether this event, this natural climate extreme, like so many weather and climate extremes, is being amped up and supercharged by anthropogenic climate change and global warming. And so let's just dig into the El Nino a little bit to understand what gives rise to these events, because we are living through one. So it's now you can be smarter than the people on the TV. And so this is an event that that occurs naturally, related to the fact that there are very strong gradients in temperature from the East Pacific to the West Pacific on normal average conditions in the Pacific. And the trade winds are fueling this temperature gradient across the basin. It sets up a very strong relationship between the sea surface temperatures across the equator and what the atmosphere is doing on top of those. And this is kind of what we call a tightly coupled system. And every few years, you kind of build up enough heat on the western side of the basin, and it becomes quite sensitive to wind perturbations that kind of like begin to tip it slightly over the edge. And we understand the physics of this quite well for about 40 years or so much so that we're able to predict these events with about 6 months lead time if we have enough information from the system. During an El Nino event, this completely changes. And so we have this cascade and basically failure of the lock between the atmosphere and the ocean, and it starts to go crippling into another cascade between the wind slowing down, the sea surface temperature gradient reducing dramatically. So now the eastern Pacific is very warm, not much different than the western Pacific. You have a collapse of the winds. You have a shift of the atmospheric convection, the rainfall into the central part of the basin. And this happens and cascades down and accelerates through November, December, January when you have an El Nino event. And then it reverses itself and you go into a La Nina phase, and then every few years you do it all over again. So this is, I'm not going to belabor this, but the point about this is that shift in convection from the Western Pacific to the Central Pacific is actually like, changing the burners on your stove. It's that important to the atmospheric circulation, and it profoundly alters the entire planetary circulation. I'm going to show you how. This is some of the effects that it has on rainfall globally. So when you have an El Nino event, you have broad swaths of the Pacific which are directly impacted in pretty significant ways. Some get wetter, some get drier. But you have effects that stretch far into North America and far into South America, and basically everywhere you go on our planet, you can find evidence of El Nino impacts. So it is a planetary scale phenomenon. And even here in New England, we have pretty profound impacts from El Nino. So here I'm showing an interesting blog post put together by some NOAA scientists looking at snowfall averages during El Nino winters. So remind ourselves, we are in an El Nino winter. So this is a snapshot of what we expect this winter to look like on average during a strong El Nino event, with significantly reduced snowfall across much of the northeastern region. So every El Nino event is slightly different, but there's that caveat. But if history is any note, this would be what we're looking at this winter. So the question that my research really drives is whether this event is being supercharged by climate change, something that is a pressing question for understanding our future landscape for extremes not only in temperature, hurricanes, rainfall patterns as well. And this is me doing my favorite thing, scuba diving in the tropical Pacific, where I look at coral records of past El Nino activity and try to compare them to the records that we have from the instrumental era in order to determine if we can detect a statistically significant change between what happened before greenhouse gases were emitted and what's happening today. We just don't have enough events from the modern era to actually be able to determine this unless we wait another 200 years, and I'd like the answer before that. So this is, we can play this game in the Central Pacific. This is a site called Christmas Island, which is smack in the middle of the El Nino zone. It's a great place to try to build these records. And I don't want to go into this plot. This is just like 15 years of my life on the screen, big deal. But, I just want to show you that these curves all look the same. And only one of those is an instrumental record of temperature. The other ones are coral-based records of temperature spanning the last couple decades. Now, this isn't providing us new information other than, wow, corals are doing a great job. But when we apply this same technique to corals from 1,000 years ago, 2,000 years ago, 500 years ago, we're extending that baseline in an extremely exquisite detail. This is one of the corals we use to look back in time. This is it's actually a subfossil coral. It's not chemically replaced, but this is uranium thorium dated to about 500 years ago. That's what you're looking at right now. And this is basically a time capsule of past El Nino activities. And you can see our drill holes right through the middle of it that we used to reconstruct El Ninos 500 years ago, giving us the first glimpse of these specific events ever obtained. And if we do this enough, and if we get thousands of years of data of El Nino events, we can actually rigorously compare the last 50 years of El Nino activity to these thousands of years of data coming from material like this. And when we do, we determine that there has been a statistically significant shift in El Nino strength from the longer pre-industrial baseline into the last 50 years. So, there's certainly a huge amount of controversy in this field right now, but so much of the paleoclimate approaches are beginning to pile on and suggest that we're already able to see a detectable signal in the strength of El Nino events today. So this is incredibly important if we're to think about folding this into the landscape of how communities and ecosystems may need to adapt to the coming landscape of change, given how impactful this event is to the global climate system. So just to close, the oceans have an amazingly important role in driving precipitation patterns and in thinking about the rate of warming and how greenhouse gases are shaping our climate of now and our climate of the future. First of all, of course, they govern the atmospheric temperature trends, which means they have a very strong role in that carrying capacity of the atmosphere that Dr. Vecchi talked about. They fuel rapid intensifications of our tropical cyclones. We've seen so many examples of this, most recently with the Hurricane Otis, but of course going back to many examples we watched in headlines in past years. And the other thing is it has, through this patterns of variability that it can take, for example, with El Ninos and how they're responding to climate change, can drive really important aspects of regional rainfall variability from place to place in somewhat predictable manners, given that we understand El Ninos coming and going, and we may be able to understand how it responds to climate change as well. So I wanted to talk a little bit about solutions because Nita was like, it's kind of depressing, your presentation, Kim. So I wanted to just let you know that when we kind of understand the totality of the science of rainfall and oceans and climate change, we can actually not just say, well, we told you so and it's terrible. We can actually put that science to work. And that's what we're trying to do at Brown University and at many other universities around the country, is use our best and brightest minds and our most refined and advanced tools to really try to make sure that we're getting that out there and helping people on the ground, decision makers, policy makers, and people who are desperate for this information. And so this is an initiative that we just launched at Brown. It's called Equitable Climate Futures, and it really seeks to put our science to work. We recognize the complexity of the problem is not just about physical climate parameters and rainfall. It's about our grid. It's about our dams. It's about our emergency response planning. It's about our weather prediction. So it's really a systems-based approach to solutions making through research and partnerships. And I'm really excited about that. And if you want to hear more about it, you can reach out to me after over email. The last thing I want to talk about is something that I'm very passionate about as a mother to four, which is a group called Science Moms. And I just think they have a great framework for helping people connect to local chapters of organizations that are moving the needle on climate action. So this is a framework where you can swap your dirty energy sources for cleaner energy sources, and the website helps you kind of think about that. You can share, you can have conversations about climate change. Research shows that as much as Americans overall care deeply about climate change, we are not reflecting that in our conversations within our networks, in our friends and family groups. So this is a lever for change, and it's important for us all to understand that 80% of Americans care about climate change and would like to see a number of solutions. Where is that at the dinner tables and the conversations that we're having in the day-to-day? And then last but not least, speak up, right? We need to see policies to advance resilience efforts. We need to see policies to decarbonize our energy sources. And it is the will of the public and the collective demands for these kinds of levers at the local, state, and federal levels that are going to ultimately get us over the finish line. So we have an active role to play in there as voters and as constituents. And I will leave it there. Thank you.
Thank you, Dr. Cobb. The word power has been used quite a bit this evening. I'm going to use the expression that knowledge is power, and you all being here tonight just picked up some more of that. And as Kim said, please go out and talk to your friends, your family, your relatives. Make that more of a normal thing. The problem can seem a bit overwhelming, maybe complex, but we know what we need to do. Dr. Vecchi showed alternative energy sources are available. Many of them are becoming more affordable. And the younger generation is making this a more important priority in their life. And every year that goes by, more people turn 18 and make decisions that have bigger determination on policy. So to gain more knowledge, we're going to now open up to some questions from the audience. And our, excuse me, our panelists here have microphones, so we can use those to get them answered. And if you're on the stream, go ahead and type it in. I have access to that there. And I believe the audience, we've had a couple mics or a microphone here that we'll go for. So I know we've got them. So who's going to be our first person? Yes, sir. We got a microphone right over here if you want to use that. Thank you.
Hi, I'm Ray Schmidt. I'm a climate scientist and entrepreneur. Started my own weather prediction company. But I was wondering about the bomb cyclone that for the Snowmageddon in Buffalo there. Was that the growth due in part to the warm lakes, unfrozen lakes? You could gain a lot of heat energy the way a hurricane gets heat energy out of the ocean from those unfrozen lakes. Did that contribute to the growth of the bomb cyclone?
I suppose there could have been some input from that. I think a lot of it probably was more upper level atmospheric driven, as a cyclone that bombs out of that variety would normally be. The thing that we talked about in our office about that event in particular that was so remarkable is normally we see these systems develop, they get into our region, and then you see some sort of, even though this isn't the right way to refer to it, a transfer to a coastal system, because the energy tends to want to go toward where the gradient in the ocean temperatures are sort of associated with the Gulf Stream. That didn't occur in this case. And what was remarkable was that the models that we use and the ensemble systems that we use tagged on this really strongly, really early. And I remember sitting in the office with all the forecasters there, and the one thing that we said, looking at these model solutions, was this doesn't happen. But all the modeling ensembles that we used indicated it was going to happen. And it's something that in my almost 20 years in the Weather Service, every different place that I've been, you just start to have to suspend disbelief that things that haven't happened before can happen now.
Thank you. Yes, go ahead.
This is a question for Kim. I wondered if you could explain a little bit more about exactly what you're measuring in the coral. It's probably like you're boring down and maybe like rings in a tree, but I'd like to know a little bit more about that.
Yeah, thanks for the question. I could go on, but I will contain myself. So what we do is we go down the coral, and every 1 millimeter, we drill a very small amount of powder, and we put that into a mass spectrometer. And what we're measuring in that mass spectrometer is the ratio between two isotopes of oxygen. One is oxygen 18, one is oxygen 16. You guys all know about oxygen 16 from high school. Oxygen 18 has 2 more neutrons, and all the water on the planet has tags, basically. And the way that the coral functions, and this is a function of thermodynamics, is that depending on the ocean temperature in which the skeleton is constructed, it actually will change the ratio of those 2 isotopes in the coral skeleton. Okay, this is not the coral making a decision. This is thermodynamics, Gibbs free energy stuff. And so this has been around for 70 years. But we've been able to apply this, and it's not just me. There are hundreds of people around the world doing this. I just did it more stubbornly than most, and really honed this into a extremely powerful paleothermometer, not just for corals, but for marine sediments, lake sediments, many other types as well. And I think it's better than tree rings because it's actually more highly resolved. We get 1 point per month when we drill a monthly resolution, enough to resolve a 6-month El Nino event, which is what we need. Thanks for the question.
That was a great question. I'm going to, please don't be shy. We got 2 mics now on each side of the room. I'll also ask Kim a question. I mean, earlier this year, the water temperatures were to the point, us at the Weather Channel, I know folks in NOAA were actually sort of questioning initially the observations, could it be? But there were just too many, over too many places, over too long of a time. Obviously, El Nino, sort of a natural event, so we can sort of expect the warming in the Pacific, when that's happening. Any ideas why this year in particular, so warm and so expansive, or is that still just an unknown?
I mean, that's a great question. So, we've seen this event coming for quite some time, as you know, with the El Nino event. But I fielded a lot of questions about, what about the North Atlantic patch? And then there was that whole North Atlantic spate of record-breaking temperatures earlier this year. And so, as happened with the so-called blob of the Pacific back in the day, it really took the scientific community a number of years to really dig into the dynamics that's causing those extended, record-breaking kind of, warmings that happen over such a large area for such a long time. So I think we'll be doing that work as a community going forward, and I don't think there are any easy answers right now, but the marine blob has subsequently, by the way, been tied definitively to patterns in the atmosphere related to climate change. So I would not be at all surprised if, as we dig into the dynamics of what's causing, for example, the North Atlantic hotspot earlier this year, and of course the tropical Atlantic in the recent months, we won't find connections back to the way the atmosphere is shaping as a function of global warming.
Yeah, great. Atmosphere and oceans
Yes.
linked together in all of their processes. Yes, we'll do your question, and we'll get to you next, ma'am.
I have like 9 questions, but I'm not going to ask them all. This was really cool. But I am wondering, not to be kind of doom and gloom, but Dr. Vecchi, you were saying in your talk, Dr. Vecchi, that even with no, even if we're at net zero, warming is happening. And I guess I wonder, when you're thinking of sort of superlative fatigue, every time that you hear a story anywhere, it's always like, this is the warmest, the most intense, the once in a generation. If everybody's hearing that, and we're also hearing that it doesn't kind of matter what we do, the climate's going to warm, then I guess I have to wonder, what's the point? What? I mean, no, but seriously, you're looking at this, the geoengineering stuff and kind of glossing over that and saying, I mean, that's sort of fringe stuff, these space mirrors and all that, solar radiation. But what else is there, honestly?
All right, so I'll start. So that's a great question, right? So what gives? And the reality is there's nothing we can do about the existence of some future warming. But we have a lot of purchase, things we do today and things we do tomorrow and the next day and the next day, have a lot of purchase on the amount of warming. And that is a really big deal. The amount of warming that we get will change the degree of difficulty to maintain and grow the quality of life that us as members of this human civilization would like to continue doing, right? To have people have more well-being, more opportunity to become the people they want to be and do all these things, right? Now, the other trend that we didn't show, but we should have shown, and I don't know if there's a number of charts in the latest Economist, if any of you get the Economist or go to the online Economist, which showed the amount globally that renewable energy has been going in. And the new renewable energy that is going in is exceeding like what anybody reasonable would have hoped for 10 years ago. Right, so there is good news there, and so what that's doing is reducing the scale of the problem we have to deal with. Not only that, I don't know if any of you saw in the news, but there was a new like the first carbon capture sort of just open air carbon capture facility opened up somewhere in Nevada, right? So that is going to be something that actively removes carbon from the atmosphere. Now that's not it's removing some small amount. But the first solar cell captured a small amount of photons and produced a small amount of electricity. And look where we are now, right? So that is technology that is being put into place, and is being put into place for profit. So if you look at some of the tax laws, the barrier to make money by capturing carbon and sequestering it has been reduced. So this is one of these places government can come in and change the game, right? And then adaptation. The Weather Service, and there's a lot of humbleness in the Weather Service about the quality of the forecast, right? Predicting something unlike anything that's ever happened before, that's a big deal. It didn't just happen with the Buffalo thing. It happened with Sandy. It happened with the Pacific Northwest heat wave. Over and over again, we get these forecasts better, right? So that is hopeful, because in a changing world, we're going to be in a better position to make decisions. Not only that, there's new materials, there's new awareness, right? This whole idea of building an equitable future, an environmentally equitable future, recognition that it is not uniformly, that the impacts of climate and weather aren't uniformly distributed, but they're concentrated in certain communities. Being aware of that gives us the tool, at least the initial tool, to start thinking about how do we make it not concentrated, right? And not by making everybody else have bad outcomes, but by focusing our effort in the places that are most vulnerable. And so I think there's a lot of reasons to be excited and a lot of reasons to be hopeful. But the reality is that we don't live in a world where on one end there's one possible outcome where the unicorns come up and we're all living in the rainbows, and on the other side is doom and gloom, but we're living somewhere in the middle. And the decisions we make will push us closer to one or the other, right? And the quality of the decisions we make come from, number one, getting better information, and number two, having better conversations, right? Having conversations where we listen to each other and where we feel comfortable, by the way, that was a great question, feel comfortable saying things that are uncomfortable, like, well, what's the point of all this? And there is a point, but we won't know the point until we ask that hard question, so.
If I could just, I want to layer one response there, because, you know, I'm a mother, and I know there are many of us who have kids and who care about kids even if you don't have kids. And so, you know, when I look at my 4 kids and the sea of students that I see at Brown, you know, what I think about, and this said this as my work in the IPCC called me to task and helped me focus on these issues, this great question about how much warming are we in for and what's the point, and, you know, is it all lost? You know, we now know that we think, and we're getting better at understanding this, that there may be less kind of baked in warming hanging around after we stabilize emissions than we previously thought. So instead of like 30, 40 years of tailed and continued warming after we get our emissions act together, the planet may be more responsive than we think. And what I would like to think, what I think about when I get out of bed in the morning is that what we're doing over the next 5 to 7 years is we're fighting to reserve the right to cool the planet by mid-century. That's the way I see it. That is within the realm of possibility right now. I mean, I may be proven wrong by the scientists in 10 years, but for right now, that's what I wake up and fight for. I can die seeing a planet that is turning the temperature curve around. So that might be another kind of thing to throw out there, and that is not impossible. And we need to reserve the right for that to happen, but we need to do that in the next 5 or 7 years. Yeah. Thanks.
Thank you. I want to ask one question based on a conversation I had actually last night when someone said, gosh, it's almost over in the hurricane season and we dodged a bullet. And then you were talking about the relationship between the Pacific Ocean and the Atlantic Ocean. I realized I don't understand that. Now, I look at weather fairly seriously because I've flown an airplane, and you have to be able to do that. On the other hand, it doesn't give you the sophistication on looking at the larger picture. So if you could talk a little bit about what it is that we should be looking at when we think we've dodged a bullet, and what the relationships of those two things are, because it's far away from us.
Well, I might defer to the National Weather Service expert on that one. I mean, this is really getting into, weather.
The hurricane forecast in particular? Is that?
Yeah, the Pacific-Atlantic relationship. Why do they, why does one matter versus the other? Why do they matter together?
They both matter.
So they both matter, right? So you've hit on something that I actually have a lot of interest in work on. So the atmosphere is connected. So there's one atmosphere. When you have an El Nino event, rainfall shifts across the Pacific from west to east, and that sends waves all across the atmosphere. One of the consequences of that is that the wind shear in the Atlantic changes. So when an El Nino occurs, the wind shear, the difference of wind with altitude in the atmosphere in the Atlantic increases. And any of you that pay attention to the hurricane forecast will know that the wind shear is deleterious to hurricane development. And so one effect of El Nino is to increase wind shear in the Atlantic. This was actually a groundbreaking paper by Bill Gray in 1984, which really sort of set the stage for thinking of hurricanes as a climate phenomenon. He recognized that El Nino tends to increase wind shear in the Atlantic and decrease hurricane activity. And so if all we had this year was an El Nino, the hurricane forecast for the season would have been somewhat easy. It's always hard, but it's somewhat easy. But simultaneous with this El Nino, we had this massive warming in the Atlantic. Hurricanes draw their energy from warm water. And so as you're increasing the wind shear, you simultaneously, the Atlantic decided to warm up. We still don't fully know why. We don't know. There's ideas. Some of it may be due to a sort of these fluctuating responses to global warming, where you have an overall trend and you have wiggles underneath, and so sometimes it looks like it accelerates rapidly and sometimes not. Some ideas that it has to do with a shift in fuels used by ships. Some of it has to do with just random fluctuations in the atmosphere imprinting themselves on the ocean. Anyway, for whatever set of reasons that we don't know now, but I promise you we will know within 2 years, which, is not going to help me now. The Atlantic got warmer, and so then what that meant is that the Atlantic is pumping the hurricanes up. So you have the Pacific pumping the hurricanes down, the Atlantic pumping the hurricanes up. In May, we saw this. And so NOAA's official forecast for the hurricane season in May was that they don't know. You have the El Nino pumping the hurricanes down, Atlantic pumping the hurricanes up, and NOAA did what a responsible person does and says, I don't know. It's probably going to be normal, right? By the time August came around and NOAA reissues their seasonal outlook, they said, oh goodness, that warming in the Atlantic went bonkers, and we think it's going to overcome the impact from the Pacific. So you have the Pacific pulling one way, the Atlantic pulling the other way, and they saw that the Atlantic had been going to the gym, got all buff, and pulled harder. And then NOAA, in August, said that the hurricane season was going to be active. And I don't know if you recall the slide, but when the hurricane activity departed from climatology starting around September, October. So that was a good forecast that NOAA recognized months ahead of time that the Atlantic was going to win the fight. And so, but this is the challenge. You have all these players going on, and actually you need to make a call. Is it going to be active hurricane season or not? Is it going to snow or not? It's a big challenge.
Sir.
I had a question about the oceans. I know when we look at these scientific papers, a lot of what we're looking at is kind of surface atmospheres. And I always kind of blown away by how much water there is under us, right? And I remember in a course I took on climatology in college, they talked about the fact that I guess if you drop water into, I can't remember where, maybe on the Pacific Ocean at the surface, it takes approximately 30 years for that water molecule to kind of circulate all the way under the water and then reappear at another upwelling event. And I'm curious, in the models, have we gotten a lot better at understanding the full dynamics of that system? You know, everything from the substructure that the Earth, you know, that the ocean currents create, to all that energy stored down there. Because it seems like when I took my course back then, it was viewed as just a big heat sink originally, I think, in the models. And then it was viewed as a big heat sink with time. What do we know about, you know, really what the ocean is doing to either enhance, compensate for the changes that we're seeing?
Yeah, so the good news is the models have gotten way better in the last 30 years. The good news for us is that they're not perfect yet, right? So we've learned a lot more. The tropical Pacific is incredibly dynamic. There is this decadal circulation. You know, if you put a water molecule in there, it's going to get caught up in this sort of ribbon of water, and it'll pop back up maybe on a time scale of decades. There's also another deeper circulation where the water that is popping up in the Pacific right now sank in the North Atlantic before the Vikings were sailing across, right? So you have to go to Tahiti right now and go deep to find water that Vikings spit into, right? And the processes in the ocean that control all these things are complicated. One of the things that seems clear is that the oceans are taking up heat as it comes in. Question is, how much of that heat can they take up? How much of the carbon can they take up? They've been taking up carbon as well. And can they continue to do that in perpetuity, or are they going to burp it out at intervals? And different models show different things. So.
Got a quick question from Katie online, hoping for a quick answer for Dr. Cobb here. Does it seem like climate change will affect how often El Nino and La Nina events occur, in addition to just sort of their amplification?
That's a good question. So the metric that we use and the metric that many of these studies have used is the overall amplitude of the cycle. You would actually need a lot more data to determine any change in the frequency of events. So it's just an easier metric for us to chase. But, you know, I think as we gain more of these records from more locations, we'll be able to bring some evidence to bear on that question, noting that those kind of answers will only come from the paleoclimate record. Those kind of answers will never come from the instrumental record of climate. They're just too few events.
Great, thank you. We'll go here, and then I want to hear from our kids over here.
In the category of adaptation, are there people doing a lot of large-scale infrastructure projects related to moving water? So thinking about the Buffalo talk, I mean, to the extent that lake effect snow is somewhat predictable, you know there are areas around there. I mean, does it make any sense from a, you know, geoengineering standpoint to build giant cisterns around the Buffalo area and pipe the water to Iowa and Nebraska? You know, why don't we move water more frequently the way we think, you know, we do with oil and gas?
Well, let me just address
Or is that all terrible from a carbon standpoint?
Let me address the local portion of that question first. You know, a lot of the cities in the Great Lakes, you know, colloquially are referred to as the Rust Belt, right? They're cities that they're not as old as Boston necessarily, but, you know, cities like Buffalo, Cleveland, Detroit, they were all started roughly 300 years ago, right? So they're cities that have infrastructure that's hundreds of years old now, that was built for a time when less precipitation was falling than is now, and that were built to distribute that precipitation that fell at a slower rate than we need them to do now. Buffalo as a city has invested in moving water inside of the city and its infrastructure more rapidly from the streets to treatment to Lake Erie, right? There are times when that system still can't handle that, and I know that's probably not unique to Buffalo, but you know, I think a lot of the solutions that both of my colleagues here have mentioned today, you can't look at a problem like that as just one big overwhelming thing. You need to start working at it piecemeal. And in the case of Buffalo, they're doing it one street at a time. And they do it as there's money, and, you know, it's not all going to happen at once. And, you know, beyond the infrastructure part of it, I think what we noticed in Buffalo was a lot of people got really lazy during COVID too. And all of these snows came right after COVID, and there was three years worth of leaves in all the drains in the city. When you have to melt several feet of snow, and in the case of, like I talked about, the Snowvember snow, that snow melted in about 10 days. The fact that we could melt that snow without a massive flood was incredible by itself. So obviously there are other portions of this, moving water to other parts of the country, that I know there's a pact amongst the states and the Great Lakes that doesn't allow that. You cannot move water out of the Great Lakes Basin. There's a pact amongst the states and provinces of Canada that doesn't allow that. So, but you may have other things to add.
I think we'll end it there, but I want to actually end all the questions with this last row of our future leaders here. So fire away, gang.
So my question was, you were talking about the El Nino and how climate change sort of is boosting its effects. Could you talk a little more about how the La Nina and how climate change affects what it's doing and its just effects in general?
That's right. So I talk a lot about El Nino because we're in an El Nino right now, but we were in a La Nina last year, and you heard it here. We'll probably be in a La Nina next year because these things, occur every few years, and there's a very strong setup right now. Almost every single big El Nino event, we always have a La Nina event right after that in the record. So you can count on that. And so La Nina is kind of the opposite of El Nino in many ways. So that's cooling waters across the central to eastern basin, and intensification of that large vertical convection that sets up over the West Pacific intensifies, strengthens. And that in itself, as Dr. Vecchi was talking about, sends its own set of waves across the entire planet and disturbs climate and weather patterns in almost exactly the opposite sense. So the plot I was showing with rainfall changes flipped the sign on much of that. The hurricane discussion, we would expect intensified North Atlantic hurricane season and a decrease in the tropical Pacific cyclone season. So with respect to your question about climate change, all we can tell from the data is that both of them are increasing because they're part of the same ups and downs of the same physical phenomenon. And so on average, El Nino events are much larger than La Nina events. And so on average, if the cycle itself is intensifying, we might expect to see kind of more punch with respect to the intensification of El Ninos in terms of our systems that are needing to struggle through these extremes, just because that's already such a larger component of the fundamental physics of the cycle. But thanks for a great question.
Thank you so much. Also, I want to shout out my science teacher, Miss Schuler.
Yay for the science teachers. Talk about a climate solution. Science teachers to the rescue.
Yeah, a proud science teacher, no doubt. Go ahead.
So I don't really know which of you this goes to, but naturally, what causes like shifts and differences in average rainfall? For instance, why does or an average precipitation actually, why does Buffalo get more snow than Boston on average? And why does, why does the Amazon get much more rain than the Sahara?
So that's a fantastic question. And you've gotten it, and our planet is so beautiful, right? It's one planet, it's a tiny little speck on the ground, and yet it's so variable. The answer to the question is going to be a little complicated, but the reason the Amazon gets more rainfall than the Sahara is that the equator gets more sun then the Earth is a sphere, and the equator gets more sun. The air gets hot there and rises, drops all that rain, and it tends to drop that rain into places like the Amazon, close to the equator. That air then, as it's rising, so imagine I'm moving away from the equator up into the atmosphere, it descends further up. And if you look, all the deserts are lined up at the same latitudes in the southern and the northern hemispheres. Right? If you can go look at a map of the deserts, they're all lined up. And that's because the air is descending from the dry upper atmosphere. And that makes the Amazon, the Sahara, and then also the Kalahari and Mexico and the Southwest US all drier. Right? And so that's one of the patterns. The Boston-Buffalo difference.
So this is one of the things that we deal with a lot at our office, and it showed up really great. And I forget which one of your presentations it was, the graphic of the snowfall deficit in El Nino years, right? And the way that I'll talk about the difference between snow in Boston and Buffalo is this: we sit at about the same latitude, right? We're at the same point on I-90, about 42 degrees north or something like that, right? So you would think that places at the same latitude would get about the same amount of snow. The problem being, though, is that we have a big body of water sitting to our west and southwest, and that big body of water becomes a source of moisture and instability that can locally affect our climate quite a lot in the winter in Buffalo that you don't have here in Boston. So we get lake effect snow every time a big gush of, well, I shouldn't say a lot of the times that a big gush of cold air comes down from Canada. Lake Erie says, well, I don't like this cold air. I'm going to spit a bunch of snow out at you. And so that's the biggest difference. The other thing, too, is that there's an influence in Boston here where you can have marine air coming back in from the Atlantic Ocean that will keep it a little bit warmer here in the winter than it probably would be otherwise. So you end up getting more rain than snow because of that.
Okay, great.
Also, shout out to Miss Schuler too. She's not personally my science teacher, but she's in charge of the 6th grade science department at my school. So also thank you for telling us to come here. This is really cool.
Listen, unfortunately, we are out of time for this, but folks, if you're by the microphones, I want you to come right at the end and just come here so you can talk to the presenters immediately after I make this little statement, which is to thank you all for being here this evening. I want to thank WBUR for a fantastic space for hosting this event. My thanks also to the American Meteorological Society and Pattern for streaming this this evening over online. This presentation is being recorded and it's available for you to watch again and share with others. And please, 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 a big round of applause for Anita Gadecki, who has put this on. It is her passion. It is definitely fair to say that if it wasn't for her, we wouldn't be here tonight. So. Now for perhaps another enjoyable part of the evening, refreshments and snacks. Speakers will be around. We'll come out there and join you all right afterwards we get our questions here up at the stage. Thank you all again for coming.